Okay, when are we ever going to have to use this stuff, Mr. Perkins? What are we doing with all these derivatives? There's got to be a reason. We can't just be finding them to find them. And you're right, and that's exactly where we're going to get started with today. And these are what we're going to be calling related rates. Related rates, changes with respect to time. And we'll put a little t in there for time because that's what we like to use. So we talked about with this implicit differentiation in section 2.5, how every function, every y is its own function of x, and we have to think about it that way. Well, the truth of the matter is the reason we were doing that was to set us up for these related rates, because every variable changes with respect to time. If it doesn't change, then we don't call it a variable, we call it a constant. So apply the derivative to related rates problems. That's our goal. And then related rates problem involving distances. I'm going to get rid of this goal C because we're not going to do it in this section. We're going to do it in the in lessons to come. So related rates. What we're going to do is we're going to start out with a function. And remember what we're doing here is we're saying every variable is a function of time. Every variable. Maybe I should even throw that in. Every variable changes with respect to time. If it doesn't change, again, we call it a constant. So when I look at this first problem, get used to this notation. Find dy over dt, the derivative of y with respect to time, if x is 1 and the derivative of x with respect to time is 2. Well, what does this have to do with everything? Well, what we're going to do here is we need to come up with an equation that relates y's with x's, so that I can relate these changes together. And this is going to make more sense after you see it happen. So I'm going to start by taking the derivative of this problem, or this y equals x squared plus 3, this relationship between variables with respect to time. So what's the derivative of y with respect to time? dy over dt. Okay, and again remember, y and x are both functions of t. Now, everything's implicit. So the derivative of x squared would be 2x, but remember x is its own function of time, so chain rule says 2x to the first times the derivative of x with respect to time, plus what's the derivative of 3? 0. So, okay, so now I've got this equation. I found it by taking the derivative of the entire equation with respect to t, not with respect to y or respect to x like we have been. Well, now what do we know? Well, we come over here and we look at our given information. We're supposed to find dy over dt. That's good because there it is in my equation. If x equals 1, okay, well, let's put a 1 in place of x, and dx over dt, the rate of change of x with respect to time, is 2. I'm plugging those values in. What's dy dt going to be under these conditions, or in this case, when x is equal to 1, I'm looking at 4 units per whatever time is. And eventually we'll have units given to us and it'll make a little bit more sense. Long story short, once you've got these variables related and you can take the derivative with respect to time, all this is a substitution problem. Under these conditions, what do I know? So it's not a hard concept once you get to the equations. It's the getting to the equations that makes it a little bit more exciting. So 2, the water gets a little deeper. The rate of change of x with respect to time if y is 2 and dy dt is 3. Rate of change of x with respect to time. Let's translate that. Rate of change of x with respect to time, that's dx over dt is what we're looking for. If y equals 2 and dy dt is equal to 3. Well, now I need to find a way. Now, one of the things that people are going to try to do is they're going to say, well, if y equals 2, then I should just be able to plug 2 in. No, that's not the case. What you need to think about is this equation is changing. It's something's growing, something's getting smaller. We'll get into the more specifics of that later. I need, under the condition of these changes, and knowing that y will be 2, to know what's happening with this dx over dt. So I'm going to start by taking this derivative. So the derivative, x times y means product rule. So x times dy over dt plus y times the derivative of x, which would be dx over dt, is equal to a 0. And now here's your equation again. Let's start plugging stuff in. dx dt is the thing I'm trying to find. Y was given to be 2, so let's plug that in. dy dt was given to be 3, so let's plug that in. The only issue that we have is, oh dear, what are we going to do with that x? Well, here's what's going to happen. If I know what y is, and I know that x times y is the same thing as 4, well, if I know that y is supposed to be 2 under these conditions that were given, I know that x is also going to be 2. So if I take that 2 and I plug it in, I've now got an equation. There's a 6, subtract the 6 over. I think your dx dt in this problem, the rate of change of x with respect to time, subtract 6, divide by 2, how about -3 units per time? So the key, relationship between variables, derivative of that relationship with respect to t, plug in what you know, see what you can find. That's related rates. Not that hard once you get through the equation. Problem 3, okay, now things are going to get a little more exciting. Find the rate of change of the distance. Now I'm a big fan of, what am I looking for? Find the rate of change of the distance. D something over dt. What to use for distance? Gosh, what a crazy thought. Let's use d for distance. So in this problem I'm looking for dd over dt. Say that a few times fast. Between the origin and a point moving on the graph of y equals x squared plus 3, when x equals 1 centimeter. Well, let's draw a quick sketch of this. Y equals x squared plus 3 would be a parabola that would be opening upward. It would have a y-intercept of 3. So there's a point on this thing that is effectively sliding along that parabola's graph. And as I do that, well, let's see. Well, it looks like that point's x-coordinate would be changing. It looks like that coordinate's y, that's y-coordinate would be changing. And here's the thing, that we're trying to find the rate of change of the distance from that point to the origin. So we're looking for the rate of change. This thing right here is what we're calling d. And that d is not going to be the same depending on where that green dot is on the parabola. So we're trying to find the rate of change of that purple distance right there. Okay, well now what do we know? We need an equation to relate everything we know. Well, we have a relationship between y and x, and y equals x squared plus 3. We have that x is 1. Is x always 1? No, because this point is moving. So if it's moving, I can't just plug 1 in because x is not constant. X is varying. X is changing at the rate of 2 centimeters per second. 2 centimeters per second. Let's highlight that. dx over dt is 2 centimeters per second. Well, okay, so here's kind of what I tell people. Pretend like that green dot is moving along that black parabola and take a picture of it. Well, when you took your picture, was that point moving? Yes, it was. Is that point always in the place it was when you took the picture? No. But when we took the picture, what did we know? When we took the picture, we knew x was 1, and we also knew some other things, or we would also be able to find some other things. So now what I really need is I need a relationship. Well, I need an equation to find distance. Well, what's our equation we would use to find distance? I could think maybe distance formula. Distance formula, that's x2 minus x1 quantity squared plus y2 minus y1 quantity squared. And if you look at the picture that I drew over here, what's one of the points I'm using? I'm using the origin. So one of my coordinates is 0, 0. So let's take that right away and let's go back to this equation that we wrote. And let's make these coordinates be 0. So what we've really got is we're subtracting 0 away from that x2 and that y2, which means we don't really need the x2 and we don't really need the y2, so we can take those out. So my distance is really x minus 0 squared plus y minus 0 squared. Or if we clean it up, square root of x squared plus y squared. Now, there's your relationship between your variables. Now, my suggestion would be, because you're about to take the derivative of that equation that relates variables with respect to time. Well, you're going to have to do a nasty chain rule on the right side. Or you could say d squared is equal to x squared plus y squared and make a much nicer derivative. 2d times dd over dt is equal to 2x dx over dt plus 2y dy over dt. And remember, we're doing implicit differentiation, so every variable is its own function of time. Well, now all you have to do is fill your stuff in. We took the derivative. We found that equation. We took the derivative with respect to time. Now we fill in our stuff. Well, what can we fill in? Well, we know everywhere there's an x, we should put a 1. We know everywhere there's a dx dt, we should put a 2 centimeters per second. We'll get to units in a little while. We know that in our equation I have a 2. I'm going to need something for a d. I'm looking for dd over dt. There's another 2. There's a 2. Gosh, wish I knew what y was. And I have no idea what dy dt is. So I'm missing a whole bunch of stuff. Well, how can I find those things? Look at the information that you were given. We were given the equation y is equal to x squared plus 3. So if y is the same thing as x squared plus 3, then take this 1 and plug it in, and you're going to find out that when x is equal to 1 centimeter, y is 1 squared plus 3, or 4 centimeters. So let's plug 4 in place of y. If we know that y is equal to x squared plus 3, then dy dt should be the same as 2x dx dt by doing a little derivative. Well, now, under these conditions, if you know that x is 1 and dx dt was given to be 2, then the dy dt under these conditions would be 4, again, centimeters per second. We'll now plug that in for your dy over dt. And the only thing you're missing is a d. Gosh, I wish I could find a way. Wait a minute. Look back at this picture that we have over here. In this picture, we know that the coordinates of that green point when we took our picture were x equals 1, and according to our calculations, y was 4. So if that's the case, I'm looking for the distance, or I'm looking for d squared is equal to x squared plus y squared. Well, if x is given to be 1, and y is, we found out, was 4, then we should be able to come up with what d is. 1 squared plus 4 squared, so d, I think, is going to come out to be the square root of 17 under those conditions, centimeters. So now take that, come back to your equation, plug it in. Well, we're going to squeeze some space here. dd over dt. How about 4 plus 32 is 36 divided by 2 root 17. I think this comes out to be 18 over root of 17 centimeters per second. Now, Mr. Perkins, should we rationalize that denominator? Whoops, I guess I should not cover this up in case somebody wants to read it. Should we rationalize that denominator? No, you shouldn't. Leave it just like that. That is an exact answer. It's a fine answer. It's just an ugly answer. And there is some heavy-duty application. What did we do? We found a relationship between the variables. We took the derivative with respect to time, and we plugged in everything that we knew. And so it's a glorified substitution problem, but that's related rates.